Last lecture, I talked about the CUFFT. Okay, I discussed the basic principles of the FFT and also how to use the CUDA library, CUFFT, to do the fast Fourier transform. Okay. Today, I'm going to talk about another CUDA library. That's the CU-BRAS, CU-BRAS. Okay. I will discuss two examples. Okay. One is the constant times a vector plus another vector. Okay, it's called SAXPY. That means summation of the constant a times a vector x, and then plus another vector y. Okay, so that's the reason the name of this routine. Okay, and also another example is the GMM. Okay, GMM is the matrix modification, and then times a constant, and then plus another constant times another matrix C. Okay, and then the result goes to C. Okay, yeah. The CU BRAS, okay, or CU-BRAS. Okay, that's an implementation of the BRAS. Okay, BRAS is the basic linear algebra subprogram. Okay, and on top of the NVIDIA CUDA runtime. Okay, and it allows the users to access the computational resources of NVIDIA GPU. Okay, so you can read the details. Okay, from through this link. Okay. Let me first talk about the BRAS, the basic linear algebra subroutine. Okay, so the BRAS was developed by the applied mathematicians at Argonne National Lab. Okay, originally, and it was a group. Okay, large group. Okay, and that start actually quite a long time ago. Began at 1960 something. Okay, yeah, and then it was before it was under another name. Okay, say that this is the ice pad or the lead pad. Okay, lean pad. Okay, so now this basic linear algebra routine. Okay, they first implement this basic linear algebra routine, and then on top of this BRAS, they developed the linear algebra lean pad. Okay, routines, and also the library for the eigen problem. Okay, ice pad. Okay, but now these two packages all merged together. I mean, this linear algebra and also the eigen package. Okay, merged together called the LabPad. Okay, linear algebra package. Okay, the power of the LabPad or LeanPad or IcePad. Okay, actually, based on the BRAS. Okay, so yeah, so if one can implement the BRAS in a very optimal way, okay, very fast, okay, for any other platforms, okay, then the computation will be fast. Okay, yeah. So so this is the basic layer of all the linear algebra computations. Okay. There's the three levels in the BRAS. Okay. There's the first is the single level. Okay. Single level, for example, this is the giving for this rotation or the modified difference rotation. Okay, and this basic vector operation. Okay, for example, swap two vectors and scalar multiply a vector and then copy a vector into another vector and SAXPY. Okay, that's what we are going to talk about. Okay, and the dot product. Okay, and so on. Okay, and then not. So this is the basic scalar and vector operation. Okay, yeah, only involve vector and the scalar. Okay, yeah. And then there's another level is the matrix vector operation. Yeah, so yeah, this is the level one double. Okay, for every level, okay, it has the single. Okay, if the data is single or double, okay, or complex, and the double complex. Okay, so the only difference is in the first letter, okay? Say, for example, the double complex is starting with D, okay? And the complex starting with C, okay? And the double starting with D, okay? And the single starting with S, okay? So from the first letter, you can easily see, okay, what kind of data type is used, okay? Yeah. Okay, so this is level 1, and then the level 2, okay? So without going to the D, C, and D, okay, you can easily replace the S, okay, by any data type you need, okay. So here, okay. So the level 2 routines involve the matrix vector operation, say matrix times a vector, matrix vector multiplication, okay, and all different kinds of matrix, okay. So yeah, so this that means the result, okay, is always a vector, okay, okay. So it's a level 2 operation. Yeah. And then level 3 is involved the matrix and matrix, okay. So matrix times matrix, okay, and then the yeah. So this is the with this vector operation and then matrix vector and also the matrix matrix operation. So this is the basic linear algebra subroutines. Okay, yeah. With such an operation, then one can write many different codes. Okay, for the linear algebra. Okay, yeah. So the cuBLAS, okay, CuBLAS, okay, is a library that implements the BLAS on top of the NVIDIA CUDA runtime. Okay? Yeah. So for example, the SGMM, okay, so this is a level 3 operation. So this is involved the 2 matrix multiplication and then times a constant, okay, and then plus a constant times another matrix, okay, yeah. So this is the A, B, and C are matrix, okay. Yeah, and then goes to a matrix C. Okay, yeah, and for the cuBLAS, okay, so it has this called cuBLAS SGEMM. So that means that this is the first head. Okay, yeah. So once you see the CuBLAS, then you know this is the in the implement by the NVIDIA. Okay, yeah. This for the single GPU, okay, and for the multi GPUs, okay, you use the XT, okay. But for not all routines are available for multi GPUs, okay, and this will, I mean, the library will be more yeah, generalized, okay. So gradually you will see many routines available for multi GPUs, okay. They are try to implement it, okay, for the complete complete all routines in the cuBLAS, okay. Yeah. Okay. The cuBLAS library has the 3 kinds of 3 sets of API. Okay. Yeah. So this API, okay. The first API is the with starting from CUDA 6.0, then you can use the cuBLAS API, and then also starting from the CUDA 6.0, you can have the XT. XT is the multi GPU, and this for the single GPU, and XT multi GPU, and also starting from the CUDA 10.1, then you can have this lightweight API. Okay. So this is a yeah, for this lightweight library dedicated to the general matrix to matrix modification, GMM operations with a new flexible API. So yeah, I am not so sure about this, the advantage of this lightweight, okay, but you can test, okay. Yeah, actually I have only used this cuBLAS API and also the XT, okay. Yeah, as I show you in the samples, okay. Yeah. If you use the cuBLAS API, then the application okay, application must allocate the required matrix, okay, and vectors in the GPU memory space. That means you have to first allocate this matrix and vectors, okay, in the CPU, and then copy it to the GPU memory space, okay. So, and then call the decide the cuBus function, and then after that you get the result, and then upload the results from the GPU memory back to the host, okay. So yeah, so all this has to be done, yeah, similar to the other I mean other CUDA code, okay, we have been using, okay, yeah. So for the XT API, okay, the application must be kept the data on the host, okay. That means you only have to declare the data, the vector or matrix, okay, on the host. And then you don't have to say copy the data, okay, from the host to the device and so on, okay. And the library, okay, will take care of the dispatching of the operation to one or multiple GPUs according to your which function to use, okay, yeah. And yeah, if you can find the required needed routine in the cuBus XT, then you should use it, okay, because it's much simpler, okay, and in most cases, okay, it will be faster, okay. Yeah. Also, if you have a system have a multi GPUs, okay, then you certainly should use the XT, okay, if such a routine is available, okay. Otherwise, you have to use the cuBus API, okay, and then in that case, it's only can be used for just one GPU, okay. Yeah. I will show you two different cases, okay. For example, the SAXPY, okay. So this is a simple kernel with one GPU, okay. So this is the Hamilton code, okay. So this kernel is, yeah, it's easy to compute this, okay. This is similar to the vector addition, except this additional scalar modification to one of the vector, okay. So there's a constant helper, okay, and then the A and B, okay. So so helper times A, and then plus B, okay, and then the result is goes to the B, okay. So yeah, so this kernel just generalized as of the vector addition, okay, we have been used, okay, yeah. And yeah, if I use the cuBus, okay, to do this operation, then I have to first declare the cuBus context. So cuBus handle, underline T handle, okay, and then initialize the cuBus context. Okay, so first this is the context, and then initialize the context. Okay, and then copy the, yeah. Suppose you already have prepared the data in HA, this vector. Okay, and then cuBus set vector. Okay, so this is the copy the data. Okay, from the host to the device. Okay, so this is different from the usual yeah, copy, okay, CUDA memory copy, okay, yeah, because you have to use the cuBus library, okay, so you have to use the cuBus set vector, okay, so this command, okay, to do this, copy the HA to DA, okay, and also the HB to DB, okay, the matrix, the vector A and the vector B, okay, from host to device, okay. And then call the routine, okay, cuBus SAXPY. So so this is the how it's done, okay. So we have the handle, and then the size of the vector, and then the constant, and then the DA and the DB, okay. Yeah. And after that, then when it's done, okay, when this operation is done, then you should copy the result, okay, from the device to host, okay? And then finally, you destroy the context, okay, destroy the Kubas context. So the code is in here, okay. There's something something wrong with the TLCP1 now, okay, and I already have my assistant going to check, okay, what's going on and see whether any hard disk need to be replaced, okay. Yeah, as soon as the TLCP1 goes back, then you should be able to see the code, okay. Yeah. So today I'm not going to do the demonstration. I cannot connect to the TLCP1 because TLCP1 is down, okay. Yeah. So I cannot do a demonstration in at the TLCP1. Yeah, for the CUDA Kubas XT, okay, then you can declare the unified memory, okay, and also using the multi GPU, okay. So for the Kubas version 2, okay, you can also use the unified memory, okay, and with the 1 GPU, okay. So this is the unified memory version, okay. So again, you have to declare the Kubas context, okay. Yeah, and then you declare the vector, okay, using the CUDA memory, CUDA manlock management, okay. So declare this as a unified memory, okay. Yeah, and then so you have to be careful about the ordering, okay. You have to first declare, okay, and then use the Kubas create the handle, okay, and then call the routine, okay. So the calling, okay, so this is the similar to what is before, but now the vector, okay, is in the with the unified memory, okay. So this is the SAXPY 1 GPU, and then the CU plus, and then unified using the unified memory, okay. So yeah, now I come to the this matrix modification, okay. So and using the multi GPU, okay, and with the unified memory, okay. So this is the code, okay, similar to the you see this is just handwritten, okay. Yeah, the most straightforward implementation of this operation, okay, without any further optimization. Okay. So you can see, okay, this is the matrix modification, okay. Yeah, yeah, A and A and B, okay, matrix modification, okay. Yeah, and then this is the, and then after that, okay, add to this matrix, okay, beta times C, okay. Yeah, so you can see, okay, the C, okay, here. Yeah, of course I use the one-dimensional representation, okay. So this is the index IN plus J, okay. Yeah, so the is declared as a one-dimensional array, okay, and actually, but it's a matrix, okay. So this the how the mapping, okay. Yeah. So this is the sum over, yeah, yeah, J from 0 to yeah, and okay, and for the I, okay, for each I, okay, yeah. So for each thread, okay, handle index I, okay, map to the index I, okay, and for yeah, and then we have the offset, okay, since I am using the NGPUs, okay, so this is similar to the vector addition, okay, yeah, for multi GPUs, okay, yeah. But here, just go through each I and each J, okay, yeah. Okay, this is the main host code. Okay, yeah. So this is allocated unified memory here. Okay, and then this is the calling the routine. Yeah, and then calling this kernel. Okay, yeah. Okay. So again, the complete code is here. Okay, yeah. I will show you the complete code. Okay, on my desktop. Okay, on my laptop. Okay, but I could not run the code. Okay, yeah, I need to connect to a TLCV1 in order to run the code. Okay, yeah. So I can use the Kubas, calling the Kubas S XT SGMM. Okay, then I can use the multi GPUs and also the unified memory. Okay, so this is the the crucial steps. Okay, outlined, others are omitted. Okay, yeah. So this is how the routine is called. Okay, yeah. Again, the complete code is here. Okay, so um, there's a handbook. Okay, for all kinds of available. How say this is the how cookbook. Okay, how to use the uh, all different routines. Okay, of the toolbars and then the lab pad. Yeah, yeah, yeah. So next week we'll talk about the lab pad and the magma. Okay, magma is a GPU implementation of the lab pad. Okay, yeah. So this example of the toolbars CU solve. Okay, CU solve is for solving the linear algebra system. Okay, and the magma. Okay, so this is the PDF file. Okay, yeah. So you can look at this file. Okay, okay, this is a big file. Okay, it has all routines. Okay, okay, so it's measured on the GPU. Okay, so so this is version is 2017. Okay, I'm not sure there must be a more updated version. Okay, I did not check. Okay, you guys can go to the web and then check it. Okay, so it gives you details. Okay, how to call each routine and give you an example. Okay, so now from here it's difficult to see. Okay, maybe I should use another. I have let's see. I can have the. I have the document somewhere. Let's see. Do I have it here? Yeah. Oh yeah, here. Then you can. It's easier to see it. Okay. But no. So maybe here. Okay. So do we see it? Do we see it? let's see. Oh yeah, you see it. Okay. So you can look at the contents, okay, and then see if which routine you need, okay, and then you can look up the example, okay. So for example, the say the Kubas SAXPY, okay, then it gives you the example, okay, how to do it, okay, exactly, okay, yeah, how to call the Kubas routine, yeah, and also if there's a unified memory version, then there's a unified memory version, okay. So all routines, okay, if it's available, then this example should have okay, at least up to 2017, okay. But in the last 5 years, okay, in the last 6 or 7 years, okay, I don't know, okay, maybe there are more updates, okay. Yeah, you have to look up, okay, whether it has an update, okay, and especially when there's a new routines available, okay, since the Kubas they continue update it, okay, especially for the XT, okay, for the multi GPU version, okay, then yeah, maybe this menu, okay, this cookbook is also updated too, okay, yeah. So besides the Kubas, okay, it also have the CU soft, okay, CU soft is the CUDA implement, okay, software, okay, for the solving the linear system, okay, so a system of linear equations, okay, yeah. So this is also very powerful package, and also there's a magma, okay, yeah, yeah. So this is the CU soft actually implement the CUDA solution for the LinPad, okay, for the LinPad. And the magma actually is the GPU CUDA implementation for the problems, okay, in the laptop, okay, or the previous package of the IcePad. Okay? So this package are very useful for any scientific or engineering computations. If you want to use the CUDA to speed up your computations. Okay, and as well as long as you can find the routine you need, okay, here, then you can look up the example and how then you can modify the example code, okay, for your application. Okay? So this is the kind of cookbook, okay, yeah, okay. Any questions so far? Yeah. So I can go to the detailed code, okay, but not only on my laptop, okay, but not at the TWCP1. Yeah, maybe I can do it here. Let me change the screen, okay, to another one. Okay, let me okay. So let me change to another window. Okay. Okay. So okay. So this is the in my on my desktop. Okay. So now, so I still have the sample code. Okay, a copy of sample code on my laptop, so I can show you the code in details. Okay. So for example, SAXP1 GPU CU. Okay. Yeah. So first I this is the routine random init allocate an array with the random flow entries. Okay, device code is handwritten. Okay, for myself. Okay, and then the rest is the quite standard. Okay, input the helper and then the size of the vector, and then the set up the timer. Okay, and then allocate the HA, HB, and the HC. Okay, and then enter the number of steps per block. Okay. Yeah. And then the CUDA malloc, okay, of the device in the device memory. Okay. And then copy the vector A and B from host to device. Okay. And then just for the timing of the input, data input. Okay. And then call the kernel. Okay. Yeah. And find out the processing gigaflops for the processing for this operation SAXPY. Okay. And then copy the results from device to host. Okay, stop the timer and so on. Okay. And compute the reference solution. Okay. And then compare the speed, okay, or between the CPU and the GPU. Okay. And then check the results. Okay. Okay. And finally, okay, feed the device memory and also the host memory. Okay. So the result. Okay. So I still have the result. Okay. So this is one GPU result. Okay. So the size vector is 8192.0000. Okay. Yeah. And the constant is the 3.1416. Okay, more or less the time. Okay. And then the block number of threads per block is 128. And then so the number of blocks per grid is so the grid is 100. So this is just choice. Okay. Yeah. I mean, this is the something I just entered. Okay. Yeah. And not necessarily this number times this number is this. Okay. Because this is a very long vector. Okay. So. And then the GPU gigaflop is 25.8. Okay. And then the for CPU for this for CPU, okay, on the GTX 1060 node. Okay, so it's not a very advanced CPU. Okay, so in that case the GPU is faster than the CPU. Okay, but not much. Okay, for this simple operation. Excuse me. And the results of the CPU and GPU that's the same. Okay, we don't see any difference. So this is for the one GPU. Okay, and now if I use the CoolBars, okay, then you can see the code for this. First I go to the SAX CoolBars using the CoolBars. Okay. Yeah. So for the CoolBars, okay. Everything else is the same before, except now here. Okay. Yeah. So I still have to allocate the vector in the device memory. Okay. CUDA malloc. Okay. And then for the copy, okay, for copy the data from the host to device, then you have to use the CoolBars, okay, routine, okay. initialize the foobar context, and then copy the vector from host to device. Okay, and you have to use the foobar set vector to copy. Okay, you cannot use the foobar memory copy. Okay, yeah, you have to use the foobar routine. Okay. And then call the routine. Okay, foobar SAXPY. And then the result is in B, okay, the vector B. Okay. And then you have to copy the vector from device to host using the foobar get vector, okay. You see, when you get the data from the device, okay, to host, then you have to use the get vector, okay. And yeah, if you have to copy the data from host to device, then you have to foobar set vector. Okay, so it's these two commands are different. Okay, yeah. Then again, compute the time and then compute the CPU reference solution. Okay, and then compare the difference. Okay, so the result is this. Okay, output. Okay. Now you see. Okay, using the foobar. Okay, the GPU is slower, okay, than the CPU, okay. So the foobar, okay, for this simple problem actually have no advantage at all, okay. It's slower than my handwritten kernel, okay. Yeah, because the overhead of this foobar, okay, is too large for this simple problem. Yeah, you see. So for this simple SAXPY, okay, using foobar has no advantage at all. Okay. Yeah. Now let's see. Okay, what happens in if I use the unified memory? Okay, see whether it is a better perform. Let me first use look at the SAXPY 1 GPU with the unified memory version. Okay, so this is the hand implement. Okay, not using the foobar. Okay, just the implement. Just change the memory. Okay, just allocate the input vector in the unified memory. Okay, could them managed. Okay, the only difference is this, and then without copying the vector from host to device. And then again using the AXPY. Okay, so this is the without calling foobar. Okay, just the unified memory version. Okay, of the AXPY. Okay, right. Okay, now the output. Okay, is the unified memory. Okay, so you see in this case. Okay, I use the unified memory. Is getting is faster. Okay, yeah. You see, compare the one without the unified memory. Okay, without using unified memory. Okay, the processing time. You see, the processing time for the CPU in this case is you see, this is longer. Okay, you see, for if I declare this as in the unified memory, okay, then the vector, okay, is takes longer time, okay, for the CPU to operate, okay. So that's reason why it takes 273 milliseconds compared to the one without declaring as the unified memory, only 202. So this 1.8 actually, okay, is not accurate. We get the speed up, okay, it's overcounting of the speed up, okay. Yeah, but if I look at for the processing time for the GPU, okay, using unified memory is 149 milliseconds, so about 150 seconds, okay. But you see, for the processing time for a GPU is only 6.3. But however, you have to take into account of the I/O time, okay. So the total time is 179, okay, compared to the 149, okay. So that means using the unified memory, okay, takes less time, okay, only 149 milliseconds, compared to the one without using the unified memory, 179, okay. Yeah. But for the CPU, okay, since the array has been declared as in the unified memory, okay, so it's not so optimal for the CPU operation. So that's the reason it took about 273 milliseconds compared to the one without declaring it as the unified memory is 202 milliseconds. Okay, so I think the a more fair comparison is both using 202 milliseconds. So in that case, okay, using unified memory, okay, still a little bit faster than without using unified memory, okay, but not by such a large margin, okay. You see this 1.8 and this 1.1, okay, and that's not correct, okay. One should use the 202 instead of 273 for the CPU time, okay. So yeah, because the decay as the unified memory, then you will make it slower for the CPU access. Okay. 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 So now let's look at what happens to the cool bus. Okay. If I use the unified memory. Okay. Let me first look at the code first. Okay. So here, just put out managed. Okay. And then yeah, and then call the foo bus routine. Okay. Yeah. So in this case, then I don't need to using the foo bar set vector, and also does not need to foo bar get vector. Okay. So here you can see using the cool bars. Okay. Yeah. Compared to the unified memory without using the cool bars. Okay. Okay. So the upper one is using the cool bars. The lower one is without using cool bars. Okay. Then you can see again, okay, without using cool bars for this simple problem, okay, yeah, is using with the unified memory, okay. So this is the 149, 150 seconds, okay, compared to 233 seconds, okay. So yeah, so you can see, okay, for processing time for the CPU, okay, that is for the, if you use the CUBA, set it using the set this memory for the for I don't know why this will be longer than the one. Okay, this for CPU and the memories are cooldown not managed. Okay, yeah, but in both cases, okay, yeah, this is the so this is the faster, this is the faster, and this is the slower. Okay, this is the one cooldown not managed, but then how come this is the this also you'll find memory. Okay, and for this code and this code, okay, should be the same. Okay, for CPU. Okay, for a CPU. Okay, they just assess the arrays, assess the vectors in the unified memory. Okay, so in both cases, okay, it should not be optimal for the CPU operation, but for the one using the CUBA, yes.
Sorry for cutting in, but I think here you only measure the CPU time for only once. Maybe we should repeat the measurement so that we can get a fair estimation for the CPU processing time.
Yeah, that could be the case. That could be the fluctuation, but seems to me the fluctuation is large, too large. You see, usually the fluctuation will not be so large. Okay.
So that may also depend on the, when you launch the code, what the computer is doing. Maybe it also has some background job. I don't know, but there could be some possibility contributing to this kind of fluctuation. So I think measure the time multiple times will give us a fair estimate for the CPU processing time. My 2 cents.
Yeah, you see, in both cases, okay, the arrays A and B are declared as in the unified memory. Okay, so after the operation, after this operation was done after this is completed. Okay, this is the using the my handwritten kernel. Okay, and this is the calling the CUBAs. Okay, the only difference is this. So so it's not completely clear to me. Okay, why for a CPU? Okay, in both cases they are accessing the memory in the device in the unified memory. Okay, but there's such a large difference. Okay, so yeah, yeah, more than 30%. Yeah, so almost 30%. Okay, so difference. Okay, so the fluctuation. Yeah, I would repeat the computation, see how it goes. Okay, yeah.
Yeah. Maybe we can draw some more clue from the measurement.
Yeah, but the point here is that, okay, for this simple problem, SAX PY, okay, you use the handwritten kernel. Okay, is faster than the CUBAs. Okay, for the CUBAs. Okay, takes longer time. Okay, yeah, but you see, okay, yeah, this is only for the vector operation. Okay, simple vector operation. Okay, but for the matrix modification, certainly, okay, yeah, using CUBAs will be much faster than your handwritten kernel. Okay, as you will see. Okay, so yeah, so for the ASXPY 1 GPU, and then the no, this is SHPY. Okay, so I get to go to the SGEMM. Okay, SGEMM 1 N GPUs. Okay, yeah. Then I test 1 GPU and 2 GPU. Okay, so let me first look at the code first. Okay, And then in this case, I always use the unified memory. Okay, see you. Okay. So this code is just the most straightforward naive implementation of this operation. This matrix multiply matrix. Okay, and then constant alpha times A times B, and then plus beta times matrix C, and then result goes to the C. Okay, so we are using the OpenMP, okay, for the multi GPU. Okay, so and this now this for the with unified memory. Okay, yeah. So yeah, this is for the single GPU, and this for the multi GPU. Okay, yeah. You can see, okay, there's an offset, and then yeah, with the N. Okay, so you have the offset, and this the upper kernel is was the one GPU, and this for the multi GPU. Okay. Okay. Now. So this is the HA, HB, and C. Yeah. For the CPU computation, I should always use the decay different array instead of using the same array. Okay. Yeah. So here the CUDA managed. Okay. So this is the HA, HB, and HC are in the device memory and in the unified memory, and for this is not in the unified memory, and this for the CPU computation, and then this will be give a better comparison, okay, than using the HA, HB, and HC directly, okay. Yeah, I mean, because HA, HB, and HC are in the unified memory, okay, so this is not a fair comparison. Yeah. Yeah, somehow when you declare array in the unified memory, then you will be tried for the CUDA point of view. You always optimize the operation for the GPU, okay, and then it's not optimal for the CPU. Yeah. So so this is just the generate the random matrix. Okay. Yeah. And so this is the kernel, okay, for the kernel, okay, using the NGPU, okay, SGMM, okay, unified memory, okay, yeah. So this is just the usual way of computing the SGEMM, okay, with a hand implemented kernel, okay, for multi GPU, and now with the unified memory, okay. So here the reference solution, the CPU solution, okay, are using the matrix, okay, in the system memory, okay, in the CPU memory, okay, not in the yeah, not in the unified memory, okay. Yeah. So compute, yeah. So this is the, okay, call this simple, okay, SGMM, okay. So this is the this is not in the unified memory, okay. So that means it will give you a more fair comparison, okay, rather than using the HA, HB, and HC, okay. Okay, and now this is for checking the difference, okay, between the CPU solution and the GPU solution. Okay, and finally clear up all the arrays. Okay, and now let me go to the output. Output. Say for example the 1024. Okay, yeah, 1 GPU first. Okay, using the unified memory. Okay, okay. So you can see the difference. Okay, so the GPU, okay, gigaflop is 25 gigaflops, and that's for CPU 2. Okay, and speed up is 11. Okay, so you can see for this, even for this very naive implement, okay, kernel, okay, not optimized kernel, the GPU already 11 times faster. Okay, of course, in this case, both CPU kernel and the GPU kernel, okay, hand implement, okay, very naively implement without any optimization. Okay, so then let me go to the 2 GPU, okay, result. 2 GPU results. Okay, here. So for 2 GPU result, then you can see the for CPU, because I only have 1 CPU. Okay, so the but for the 2 GPU, seems the performance not so good. Okay, you see. Yeah, let me go back to 1 GPU. Okay, for 1 GPU, this total GPU time. For 2 GPU is this. So yeah, something is not something seems not quite right. Okay, because the total GPU time for the 2 GPU is this. Okay, and for 1 GPU is this. Okay, so there's so using 2 GPU in this case seems slower. Okay, that is something yeah, and we do not see in the case of the vector addition. Okay, but this for the matrix multiplication. Okay, so and you can see in both cases the normalized not is the same. Okay, that means the operation, yeah, is the results are compatible. Okay, compared to the CPU solution. Okay, so you see this SCMM using this simple kernel. Okay, using 2 GPU, the performance seems even lower. Okay, so there's something, yeah. We should aware something like this could happen. Okay, if you don't optimize the kernel, and using 2 GPU, okay, would be getting slower rather than speed up. Okay. Yeah. Now let's go to the coupons. Okay, using the coupons, SGMM coupons. Okay. Yeah. Okay. So this is only for the CPU. Okay, you routine. Okay, and this is the for the coupons. Okay, and yeah, it's very simple. Okay, yeah, you don't have to do anything about the yeah. You only declare this CUDA memory managed. Okay, in the unified memory, and then yeah, select the devices. Okay, yeah, for this CUBA's XT operation. Then allocate this unified memory. Okay, unified memory. Yeah. And then generate the random matrices, okay? And then call the Kubas XT routine, okay? Yeah, perform operation with Kubas. Okay? And then that's it, okay? And then, yeah, you don't need to say, yeah, yeah, get the data, okay, get the results, okay, from the GPU, okay, because in the unified memory, okay, and okay, and then compare results, and then compare the performance, okay, finally clear up all the vectors, clear up all the matrices, okay. So let me look at with the Kubas, okay, one GPU, okay. So this is the without the unified memory, okay. Okay. And you can see, okay, there's a dramatic difference between the CPU and GPU performance, okay? Yeah. So this Kubas-XT, okay, for this matrix modification, okay, constant times a constant, and then plus another constant times another matrix, okay, SGA-MM, okay. You can see, okay, the time is only 16 milliseconds, okay? Yeah. And for the CPU is this, okay. So the gain is 94. But what happens to the yeah, not full bus, okay, but just one GPU? No. Unified memory. Okay. So you can see, okay, so for if I use this simple kernel, okay, then I have this 128, okay, milliseconds, okay. If I use the Kubas, okay, let's see, one GPU. Let me see, use the unified memory, okay. Then using unified memory, okay, here, speed up for one GPU is 386. Let me see the time, okay. The time for CPU is this. The time for the CPU is this, okay. Let's see, this is the one GPU unified memory, okay. I had two runs, okay, so different ones has a slightly different results, okay. Yeah, this is the 8762 millisecond for CPU, but then this is 8300 millisecond for CPU. So it's the difference, okay. But for the GPU, okay, it's more or less the same, okay. This 20 and this 21. So the gigaflops is 155 and 149, okay. Yeah, and this for using the Kubas, okay. But if I compare it to the one GPU, okay. So you can see, okay, there's a performance is for the handwritten kernel, okay, self-implemented kernel, okay, naive implementation without optimization, and the time, okay, is much longer, okay, it's 120 milliseconds compared to 21 milliseconds, yeah, or 21 milliseconds, okay. So you can see the Kubas is the much really highly optimized kernels inside, especially for the matrix modification. Yeah. So let me go to 2 GPUs. Okay. Okay. For 2 GPU, okay, yeah, for the handwritten kernel is slower. Okay. Yeah. But let me compare the two bars, 1 GPU and 2 GPU. Okay. And the 2 GPU. Okay. So for the 2 GPU, let me see. This is for the 2 GPU 20 milliseconds. And this is the 23 milliseconds for 2 GPU. So the 1 GPU and 2 GPU in this for the two bars, okay, is more or less the same. Okay. Okay. Yeah, I think that's because the GTX 1060, the communication between these two GPU, okay, is not fast enough. Okay, not very fast. Okay. So the 2 GPU performance and the 1 GPU performance for the two bars more or less the same. And for the handwritten kernel, okay, 2 GPU even have a lower performance than the 1 GPU. Okay. Okay. But you can see, okay, the performance of two bars is really quite yeah, outstanding. Okay. Yeah. And yeah, I think no matter how you do the optimization, okay, it's very difficult to beat the performance of the two bars. When it comes, if there's a routine, okay, if there's operation, okay, which can be computed by the two bars routine, okay, especially the XT, okay, the one with the multi GPU, yeah, and with the and that you should use the Kubas XT, okay, yeah, okay, yeah. For the multi GPU performance, I think it depends on the GPU, okay. So for the GTX 1060, okay, the system itself, okay, without this NVLink, okay, without the fast communication, then the performance will be much degraded, okay. So I think with the say with the NVLink and then the multi GPU, the performance will be must be more, okay, higher than the single GPU. Okay. Yeah, yeah, I think I can perform such a demonstration, but not in the TLCP1. Okay, then I have to use another system. Okay, with the NVLink. Okay, say with the RTX 3090. Okay, then it has the NVLink connected to it to two GPUs. Then in that case, I can demonstrate the 2 GPU performance. Okay, with the cool bus. Okay, actually runs faster. Okay, yeah, maybe I can do it next time. But I cannot allow you to use this this RTX 3090. Okay, because it has been used for running my other computations. Okay, this is the 24-hour, yeah, I mean day and night. Okay, continuous simulation of the QCD code. So, but I can stop the computation, the simulation for a while, just for this class, for this the demonstration between these 2 hours. Okay. Okay. So now if I go to a larger matrix, okay, say with the 2040 by 2040, okay, matrix and random matrix, then let me check the performance with the 1 GPU and then with the 2 GPU. Both are calling the two bars. Okay. So for two bars, for the this is the okay. So the time is 70 for 1 GPU is 75 milliseconds. But for the two GPUs, 204. Again, okay, using two GPU has no advantage at all. Okay, at least for this system. Okay, yeah. So yeah, if you don't have a fast communication between two GPUs, then I think, yeah, especially for these libraries, okay, it won't give you a better performance. I guess this is in general true. Okay, unless you have the NVLink fast communication between two GPUs. Okay, yeah. So these libraries, unlike the one we use, say, for example, for the Laplace, okay, equations, for solving the Laplace equation with the Jacobi algorithm. Okay, and in that case, okay, yeah, we using two GPU is faster than using one GPU. Okay, yeah, about 1.8. Okay, faster. Okay, yeah. So yeah, but for this Kubas, okay, so I think the implementation, okay, was has been geared for the two GPU with the high speed communication. Okay, so it's not optimized for two GPU connected with the PCI bus. Okay, so, okay. Yeah, so I have several different ones, okay, and there's some old one test data, okay, so test one data. Okay, so these are the old tests, okay. Any questions? No? So these are the group bars and the yeah. Yeah, I'm not sure now whether I can connect to the server TLCP1. Okay, let me try. Okay, let's try see if I can do it.
I think it is working now.
Oh, okay, good. Okay, now okay, then I can go to the TLCP1. Okay, to do it. That means my assistant has been fixed it. Okay, at least we put the system. Okay. I don't know why the system was down. Okay, I only until this morning I see it's down. Okay. Okay, now let me connect it to it. No, let me first turn on the. Let me see. Okay. Now let me connect to the connect here. Okay. So let me. Let me see. Check. Okay, now I can share the screen. Yeah. Okay. Let me exit this screen and then connect to another terminal screen. Yeah. Okay. Now you see it. Okay. Now you see it. Okay. Let me see. Okay. Okay. Now I have to copy the command file from the NGPU. Okay. And then here. So I have to change the SAXPP. XP1. Okay. Let's see. I have to say which SAXPY 1 GPU. Okay. Okay. So I have to change this. One GPU. Okay. Okay. Now I have to okay. Let me see. So I have to change this GPU ID 1. Okay. So now I can input. Okay. G1. Okay. So now it's begin to compute. Yeah, it takes some time for the condo to start the job. the initialization process seems too long. Okay, you see, it's still initialized. Is it working? Is the system working? Oh, something is wrong. So the console, yeah, I think the console is still not working properly. Yeah, let me debug. Let me see. Only up half an hour. So yeah, I think the console still has some problem after reboot. So something still not quite right. Okay. Yeah. Output 1 GPU. Let me see. Output G1. Output G1. There's no output G1. So yeah. So console out. Let me see. SAXPY 1 GPU. Oh, I have to. Name is different. SA. Okay. So I to. There's a typo here. 1 GPU. 1 GPU. I have to type it. Okay. Okay. Now this time should work. No. G1. Oh, I also have another typo. This not here. It should not be here. This one is okay. This is 1 GPU. 1 GPU here. But then the executable, okay, here. Should be 1 GPU. This is little letter, small letter. Okay, so this is my typo. Okay, now. G1. Okay, now this time should work. Yeah, it's running, okay. So it should be done now. Yeah, okay. So let's see output. Let's see. G1. Okay. So the speed up of the CPU, okay, with the handwritten kernel, okay, for the SAXPY is 1.0, okay. Compared to the 1 GPU before, okay. Let me see. Processing now for GPU now is faster because maybe the and then the GPU performance the same, okay, more or less the same, okay. So now this the performance, just the CPU difference, maybe the CPU is different, okay, yeah. Okay, now let me try let me see. Let me first make pin first, and then we make everything. Using the 2 GPU and see how it works, whether it's getting slower. Okay, now let me use the G2. Oh, I don't have the 2 GPU version. Right? Yeah, this is the 1 GPU. So only have 1 GPU. So let me. Yeah, for SAX PY is only have 1 GPU. Let me check. Okay. Yeah, I only have the 1 GPU version. So let me go to the SEMN and GPU. Okay. So let me make it. Okay. Okay, now copy. Okay. Let me do the G1 and using the S and GPU, you SGMN and GPU. SGMN. And GPU. And then using the unified memory. Okay. Okay. One GPU with unified memory. Okay. And this is the with the input G1. G1. Okay. Okay. Yeah, for a condo, I have to give it the GPU ID such that it will assign the device number itself. Okay. So this is the option for the unified memory. So now, okay. So let me submit this now. G1, okay. Okay, now let me compare the one using the toolbars, okay. Okay. in GPU. Yes, done. Let me look at the output G1. Okay. So speed up of one GPU is 10 in this case. So this is the time for the CPU, and then the total GPU time. Okay. So now let me use the coupons. Okay. And GPU coupons. Okay. G1 coupons. So I should have so let me step down. Let's see. Yeah, I think that's it. Using coupons. Oh, hey, someone is submitting homework. Hmm? Yeah. I don't know, there should be two nodes, okay. You should go to another node, okay, but it seems now tab. Oh, homework 5 tab, okay. So yeah, about your question of the using the 2 GPU of the using texture for the 2 GPU for the Laplace equation, okay. Actually, I have looked at this problem. It turns out the using texture for 2 GPU turns out to be slower, okay, than the CPU, okay. So so this I mean slower than without using the texture, okay. So that means for the N GPU, for the 2 GPU, at least for the GTX 1060 system, okay. So texture, if I use the 1 GPU, okay, using texture, okay, is faster than without using the texture, okay. However, for the 2 GPU, okay, turns out is slower, using texture slower than without using texture, okay. So
Okay, I see.
yeah, so that's so far my code, okay, can only attend such a, I mean, the result is the same, okay. The result is, in your case, okay, you don't get the correct result, right?
Yes.
Have it, yeah.
So
yeah,
okay.
there's some problem of your code, some bugs of your code, okay. Yeah, I can show you my code, okay, with the texture, okay. Yeah.
Okay.
And then you can see if you can make it using 2 GPU, using texture, whether it can be faster than the one without using texture, okay? Okay, you can try, okay?
Okay.
I tried it for a while, okay, but seems to me it's difficult to make it faster than one without the texture, okay? Yeah, for 1 GPU, certainly using texture for the large lattice, okay, would become faster, okay? Yeah.
Yeah.
Yeah, I will put it in the sample code, okay, and then you can test, see you can tune the code such that using texture will become faster even for 2 GPUs, okay?
Mm-hmm. Okay, I see. Thank you very much.
Okay. Let me look at the result. Okay. Output G1 for cool fast. Okay, you can see, okay, it's much faster. Yeah, so with cool fast compared to with using the handwritten, okay, kernel, okay, yeah, for the just for the for GPU comparison, okay, time for one GPU of 32 milliseconds, okay, using the cool fast, okay, and without using cool fast is 139, okay, so you can see, okay, there's a factor of say 4, okay, yeah, about over 4, okay, difference, okay. So this is the gigaflop, in terms of gigaflop is 23, and this is 98 using the full bus, okay. And just forget about the CPU performance, okay, because in this case, it's not the for this is slower, okay, CPU, and this is faster, okay. But just compare the GPU performance, okay, you can see the yeah. The node, this is seems a little bit larger. In both cases, we use the unified memory, okay? Yeah. So, let me see. With the CMP G1. Yeah, use the unified memory, okay? So, so the full bus has a slightly larger error than the one. I think that might be some. Yeah, the one without using the coupons. The one with the using coupons is the lowest not error is yeah, but the size everything is the same. So I don't know what caused the difference. Okay, yeah, using coupons. Okay, yeah, seems have a slightly larger error than the one without using coupons. Okay, so yeah, you can look at the. I think the code is the same for the CPU. Okay, so let me see. See if that is the same for the previous result. Yeah, good pass. GPU. Yeah, you see before is the same. Okay, so this is the result before, and then now today, okay, is the same as the result today. So yeah.
Yeah, but is the error in a acceptable level in this calculation? Like a 10 to minus 7 seems to be good precision, like a better.
Yeah, it's good precision, okay, but there's a still difference, okay, that slightly bothered me, okay. Yeah, presumably they have the same standard, is it? Yeah, I think yeah, you see the Kubas, they use the IEEE standard, okay, and maybe for the one computer with the I mean, without using the cool bars, okay, just use the Linux, okay, yeah, GCC, okay, or the CUDA. Actually, this is a CUDA, okay, yeah. So both are using the CUDA, okay, but yeah, just one is using the library CUBAS, the other one is using the CUDA. So presumably both have the same IEEE standard, okay, but but there's some difference, okay. Yeah, that's something I don't understand. Yeah, because it involves the CUBAS, there is a black box to me, okay. Yeah, yeah, and yeah, the optimization they use, okay, is quite obscure, okay. It's not easy to trace everything, okay. So
okay.
I don't know what has caused the difference, okay. Yeah, but I guess, okay, such as minor, a small difference, okay, would not matter, okay. Yeah, yeah, because it's already very small, okay, error for the single precision operation. Maybe some operation, okay, yeah, depends on the reordering or anything like that, okay, yeah. When they do the optimization, they often reordering some operation, yeah. Of course, all these discovery yeah, can compute, okay, all these operation, okay. But the end result may be different, okay, yeah, so.
Is the error here the sum of the difference for all the elements in the matrix?
Yeah. You can look at, okay.
Yeah.
Yeah, you know, okay.
For individual element, I think they are good enough.
Yeah, for individual one, okay, that's good enough. I think so. Yeah, this is you see the error, okay. The knot is this, okay. So this is the difference for each element, okay, and then add up together, okay. The square it, okay, and then and then okay, this is the error, okay. This is the matrix, okay, and this computed from the GPU, and this is from the CPU, and the difference. So for each element, okay, and sum together, sum all the errors square, okay, yeah, okay. So yeah.
Yeah, and the resulting error is at the level of 10 to minus 7. To me, this is really precise.
Yeah, I think so. I think there's this is the knot, okay. This is the error knot, okay. Yeah. So I think there is quite acceptable. Yeah. So this is this one divided by this, okay. Yeah. So this is these two error, okay. One is the so this is the error. Yeah. Okay. I think it's good. I think it's good enough. Okay. Yeah. One should not be bothered by the 10 to minus 7 or 10 to minus 8. Okay. Yeah. Okay. Okay. I think that's all. Today. Yeah, the lecture. Okay. So next time I'll talk about the how to use the magma, okay, to solve the eigen problem. Okay. Yeah. Okay. The eigenvalue. Okay. And also the eigenvector. Okay. But I would mostly focus on just getting the eigenvalue, okay, in my sample code. Okay. Okay. Yeah. Do you have any questions? Okay. If there's no questions, okay, then yes.
Excuse me, I have a question.
Huh?
I have a question.
Can you repeat it? I could not hear you.
I have a question.
Yeah. Please ask.
Like yesterday, I tried to connect to the workstation, but I cannot connect. And right now, I can connect again. So, is there any problem with the workstation like in the weekend?
No. Can you connect now?
Yes.
Okay, but I don't know why you could not connect yesterday. Okay.
Yeah, I cannot connect yesterday.
I don't know why. I don't know what happened to you yesterday. Okay. I always has no problem to connect to it.
Okay, thank you.
Okay, yeah. So I don't know why. I don't know why you could not connect it yesterday. Okay. Yeah. How long was it?
Like I don't know. Like I have some problem like in Saturday and Sunday, but now it's quite well again. Now there is no problem, but there is some problem.
Okay. Yeah. Next time when you have a connection problem, let me know. Okay.
Okay.
Yeah. Okay.
Okay.
Any other questions? Okay. If not, okay. See you all next time. Okay.
Thank you very much.
Okay. Bye bye.
Teacher.
Bye bye.
Bye bye.